proposing to put in place to go digital. So digital, not in the sense of automated mobility, not in the sense of mobility as a service. No, we're going to hear about how digitalization can be used, can be put at work for developing vehicles in general, for developing electrified vehicles in particular, and I would say even more in particular about the development of complex electrified platforms. So the 3 projects were launched at the end of 2018, beginning of 2019, when electrification was already a big thing. Since then, as you know, the technology and electrification has been identified by all major stakeholders, and I think here about the Commission, about the I think about the scientific community, and I think about the industry as one of the key enablers to achieve climate neutrality. And we hear this morning about the directors of the European Commission that the European Commission has a big plan for us, which is the Green Deal, and that is a plan to make Europe climate neutral by 2050. This is going to be challenging for transport. Transport represents one of the major shareholders in terms of the total greenhouse gas emissions, and it is also a sector that in the recent years has seen an increase of the emissions. So if we want to invert this tendency as soon as possible, and if we want basically to have in 25 years' time a fleet of road vehicles which are almost entirely zero emissions, we need to speed up the development of the platforms for electrified vehicles. We need the tools to cope with complex architectures. And I think here in particular to the heavy-duty vehicles, but this is something that we can discuss later on during the Q&A part of the session. We need to develop quality electrified vehicles which are affordable and sustainable. So this is, in a nutshell, the goal behind the 3 projects that are going to be presented this afternoon. Another interesting thing about the project that I would like to share, so the 3 projects basically belong to the same topic. As we said, they share the same goal, but as we will see together, they went along 3 very different perspectives. Project Panda worked very much on the organization of the models in the cloud. Project Vision XCV focused on the development of virtual components and their integration into the system. And XIL4EV work on real testing using remote and distributed X-in-the-loop testing platform. So you see 3 different approaches in the end for reaching a common goal. I'm not going to spend additional time on the project, so the coordinators are there. They will present you the project. So I'm going to stop here with the introduction, and I propose that we start with the presentations. So I'm going already to introduce you the first speaker, Alain Bousquerolles. So welcome, Alain. So Alain received a PhD in electrical engineering from INP, Toulouse, France in 1995. He is professor of University of Lille, France, coordinator of CUMIM, interdisciplinary program of the University of Lille, co-director of the International Research Lab eCampus on Sustainable Mobility. He is, as I mentioned before, coordinator of Project Panda, general chair of the steering committee of IEEE, Vehicle Power Propulsion Conference. His research interests are in control of electric drives, electrified vehicles, and hardware in the loop. As part of his professional career, he has been involved in collaboration with PSA, Peugeot Citroën, with Renault, with Siemens, SNCF, and Valeo. Welcome, Alain. If you're ready, the floor is yours.
Thanks, Eric. Okay. So, hello everybody. It's my pleasure to present the nice project Panja. Nice logo. I hope a nice project too. We have a consortium composed of 11 partners from 6 countries. You can see that we have 4 universities, 4 companies, industrial companies, and 3 SME. In order to develop a new way to test electrified vehicles and components. So first, some idea of the concept of the Panda project. So for the development of electrified vehicles, we can use what is called the V model. So in the green axis, there is a development phase from the vehicle subsystem component. So there are a lot of studies to develop the right component for electrified vehicles. After the design of the component, we have to realize the component and to test the component in the orange axis. If the component is okay, we can integrate in the subsystem. If not, we have to redesign that. And step by step, we can build a real prototype of the vehicle before the production. So as said by Eric, nowadays there is more and more simulation tool, this digital tool, in order to help and to fast the development of that. We can see in purple that there is a new axis which is called virtual axis. The idea of virtual axis is to replace a real prototype by a complete simulation of the vehicle as accurate as possible. And also in the real testing, nowadays we use what is called hardware-in-the-loop testing, which is a combination of real component and software in order to test the component as in the real life using real-time models. So in the Panda project, the aim is to develop a new method to organize all the models within the V model of development of vehicles and to put that models in a cloud in order the different task supplier and so on can use that model to develop their component or their vehicle and so on. The main objective is to reduce the lead time of development by at most 20%. So you have globally the idea here. After modeling the different components using mathematical models, we will organize the model with the EMR formalism. EMR is a graphical tool, energetic macroscopic representation, to organize all the models in a unified way, thermal models, mechanical models, electrical models, and so on. It's a very specific organization, and it can lead systematically to the control scheme of the system. In the blue part is a mirror effect. There are some rules. And in this project, as a demo, we use AMSIM software from Siemens, where they integrate a new library using that method in their software, and we can simulate different kinds of vehicles. So the results, first, the different partners develop different models of the different components. Thanks to the approach, what is important is in each component, all the time within the development process has the same input and outputs. That means that we can change the model, a simple model by a more complex model, a very complex model within the complete simulation of the system. So the flexibility is very important, and we can develop multi-level model for each subsystem or component using the library. So we develop many models, and we put the models in a cloud, and we can use that models to simulate different topology, different complexity with different accuracy of the model. So we do that for the Renault Zoe, a battery electric vehicle from Renault. A fuel cell vehicle from another European project is Movipost, and also a demo car from Valeo company, which is a plug-in hybrid electric vehicles. And we get a very important accuracy comparing to experimental tests on the vehicle. I just give you one example. Is the example of the Renault Zoe from Renault company. They do a lot of driving cycle, real driving cycle on the test track in T2 in Romania. We record all the data and we redo the same driving cycle using the simulation and we compare the results. As you can see in this slide, we compare the state of charge of the battery and the energy consumption, and we have an accuracy of 98% for any driving cycle, highway, urban, and so on. That means that this model can now replace some real tests on the real vehicle. And of course, we can gain time for the development. Not all the tests, but some. Moreover, using the cloud, we have tested the different components of the demo car of Valeo using the hardware in the loop techniques. So we test one component in interaction with real-time model of the other part of the system. So with Typhoon, we built a real-time simulator with a connection directly with the cloud. And we have tested the battery, which is a new battery developed by Blueway company, a new electrical drive developed by Valeo company, and we have also tested all the electrical subsystems connected together in order to know if this set can have the right performances. I just give you a short example. So we test the battery in Brussels at VUB. We test the battery with a power amplifier, which is managed by the simulation in real time of the complete vehicle. And this simulation is split in two parts. One part is running in real time in a local ECU, the real-time computer, and one part is also running in real time in the cloud with real-time exchange with both. And we can check if the battery behavior is okay, what are the limits in temperature, what are the fault when there is a fault management, and so on. So now some perspective. First, we have built an evaluation group with other companies and Panda company, and they will test the methodology for their own system. These systems are not the systems that are studied in Panda. It's mandatory to have a new system. So Sherpa company is simulating a fast charging station. Singular company is simulating the retrofit of a gas ship in electric ship. The Metropole of Lille is testing its future automatic subway. SNCF company is testing a new hydrogen train. And the University of Applied Science in Western Switzerland with a local company is testing a new electric locomotive. And they will give the feedback from scratch because they don't participate to the project and they use the tool. So what are the perspectives? First, we are discussing with Siemens on a business model to integrate this new library into SimCenter AmSim. They develop specific tutorials because it's another simulation philosophy. Tutorial from the EMR, tutorial for the cloud. The education version will include systematically the EMR library, and we are discussing to include the EMR library in the classical industrial version of AmSim. But we are also working on other software like MATLAB Simulink. It's not dedicated to one software. There are some PhD students that was involved in Panda, and they aim to develop a spin-off in order to help the company to integrate this new philosophy of simulation and to contribute to a faster transition to e-mobility. We have other applications than transport today. We use that for renewable energy conversion system. Maybe we can extend to heavy trucks, positive energy building, and so on. And we contribute to other call of Horizon Europe. And what is also important for us is also to train the future engineers in that philosophy. That's why we apply to Marie Slowodowska-Curie Action Doctoral Network in order to transfer that, to extend the tool to other items, and also to train future engineers, because we know that we have to train people to do the transition. So it's my pleasure to welcome you at the final event. So we have the final event 24 and 25 of May. Of course, there is a presentation. There will be presentation from the Panda members. It will be online and on-site, both together. We have the pleasure also to include XL for EV and Vision EV. We work together. We have some common workshop together with Valentin and Reinhardt and Upscale. And also the company that is testing nowadays the method will be present to give a presentation and feedback on the method. So if you would like to join us, you can go to the website and to pre-register, online or location. Thanks for your attention. I will give the floor to the next speaker.
Okay, thank you very much, Alain, for the presentation and for sharing what you have been able to achieve so far. I think you talk about the interesting application of the innovation which has been developed as part of the project, and already you show good exploitation potential of what has been developed by Project Panda. So thank you for the presentation. So I'm going now to introduce our next speaker, so Dr. Reinhard Thatch. Rainer is going to talk about Project Vision XCV. Rainer is Principal Research and Technology Manager at the Business Unit Advanced Simulation Technologies of AVL in Graz, Austria. He received a PhD from Graz University of Technology and joined AVL as a research engineer in 1991. In 1999, Rainer took over the responsibility for the CFD software development activities. Since 2012, he has been holding the current position, which comprises initiation and coordination of collaborative research and technology projects with industry and academic partners. His current main research interests are with the future mobility and electrification topics, as well as related simulation tools, methods for the combined virtual real product development. Thank you very much, Rainer, for being here with us. So the floor is yours.
Thank you, Eric, for the kind introduction. And and a warm welcome and good afternoon from my side. It's a pleasure to be here and to give you an overview on the Vision XCV project with its full title, Virtual Component and System Integration for Efficient Electrified Vehicle Development. Let's start with a few key facts of the project. It's running established under the GV02 2018 call and started in January 2019 and was finished in December 2021. The consortium comprises 14 partners from 10 European countries and is involving 3 OEMs, is involving hardware, software engineering suppliers, and a number of universities all over Europe. The budget was 4 million euros, and the coordination was taken over by AVL with its headquarters in Austria. Well, the overall objective of the project was to establish or elaborate a generic virtual component and system integration framework to facilitate development efficiency gains of larger 25% for all kinds of electric or electrified and hybrid vehicles. That was broken down into several technical goals, namely to reduce the experimental parameter identification work for model calibration, model parameterization, to generally reduce system modeling and parameterization effort by developing specific and dedicated workflows and by utilizing the experimental data provided from the experimental work. A large portion of the work was devoted and aimed at increasing the efficiency and reducing the effort for model coupling, co-simulation, and bringing down the complexity and speeding up the process of integration of models to set up a system simulation environment. And and also the model prediction accuracy increase and increased extension of the extrapolation capabilities of individual models was one of the major goals in the project. The work was split into several work packages elaborated by different groups in the projects, and there was one group was specifically working on the electrical energy storage components, battery, supercapacitor, and electrical energy conversion components, different types of e-machines, power electronic devices, in order to develop models, multiphysics-based models with inherent predictive capabilities, really bringing in, combining the multiphysics nature of the electromagnetics, of thermal, of fluid flow effects, and to utilize efficient simulation in a holistic manner. On the battery side, specific experimental characterization workflows have been built up and extended into the direction of enabling seamless import of parameters into multiphysical models. A similar approach was chosen for modeling of the power electronic components, where also the starting point was the multiphysics simulation, the 3D multiphysics simulation of the detailed electrothermal behavior of the power electronic components in this kind of inverter components. In order to bring all these high fidelity models into a system environment or system simulation approach, model order reduction technologies have been developed and applied in order to set up real fast and real-time capable models derived from the detailed high-fidelity 3D multiphysics simulation results. So the outcome of this bunch of exercise, bunch of activities and tasks are a set of highly accurate and scalable e-component models or component models of the electrical, main electrical components and subsystems in the eDrive. Since we have been dealing with hybrid vehicles, with different types of hybrid configurations, also the classical internal combustion engine with charging and after treatment components and subsystems was considered here, and research and innovation activities were devoted to the specifically to the to increase the predictive accuracy of the transient engine dynamics behavior, integrating or directly integrating innovative models of advanced charging devices, taking into account, again, the multi-physics nature of flow thermal effects. And here, novel exergy-based models have been developed, increasing the predictive accuracy of the charging models far beyond what was available before. Regarding the after-treatment activities, catalyst heating and technologies related to phase change material have been investigated, and models have been set up and developed for integration into these combined engine charging system and after-treatment modeling complex. And as a result of these activities, high-fidelity, fast IC engine turbocharging and exhaust after-treatment component models were developed utilizing different software tools, in-house tools of the partners, and also commercial tools, which were then used in the next phase of the project, namely in the integration of all these models to establish the scalable multi-physics component and system integration framework. So all the different high fidelity or reduced order models parameterized based on experimental and high fidelity simulation results have been coupled and interfaced to seamlessly work together regardless of the partner from whom these models originated from, regardless of the modeling platform. So that was the specific goal here, to enable interfacing technologies and workflows that allow a seamless exchange of different models regardless of the modeling platform. And different framework building blocks have been established here by the partners, dealing or addressing a vehicle concept layout, addressing the internal combustion engine, exhaust after-treatment integration, and also with thermal networks, so cooling flow and oil flow networks. Thermal analysis framework was a major building block in all that, especially related to hybrid vehicles, pure battery electric vehicles, where the cooling, the thermal conditioning of the battery, of the e-components, of the e-machine, the power electronic, is decisive also in the context of passenger cabin heating, air conditioning, ventilation, especially with respect to the achievable driving range of hybrid vehicles, of plug-in hybrid vehicles under pure electric driving modes, and especially battery electric vehicle driving range under severe ambient conditions like low temperature, for instance. And in addition, partners were also working on hybrid electric vehicle controls framework in order to support the layout and calibration and parameterization of hybrid control units. So the outcome of that activity is the virtual component and subsystem integration methodology, which was then used by the industry partners to demonstrate and perform the impact assessment on the basis of 4 use cases. So one of these use cases was related to battery pack thermal analysis and optimization. Another use case use case cluster is probably the better word, was was related to different kind of hybrid and pure battery electric vehicle. There was third use case on the matching of the internal combustion engine with a post-Euro 6 after-treatment system for a plug-in hybrid electric vehicle. And the industry partner, FPT, was working on a use case or was providing a use case of a heavy-duty urban bus hybridization exercise in order to apply the Vision XEV framework. So in short words, so in use case one related to the battery thermal management system, a digital twin of the battery system, including its integration into a passenger car plug-in hybrid vehicle, was set up, and using the components provided by the partners, specifically the battery models and the battery system, and several engineering exercises, simulation exercises, have been performed with respect to parameter variations of the cooling strategy and the packaging of the battery cells. Use case 2 was actually looking at 3 different configurations. So one was related to a plug-in hybrid electric vehicle where the hybrid transmission model provided by one of the partners was intimately linked with the e-machine models developed and by University of Ljubljana, and this use case was then further devoted and looking at the impact of different hybridization strategies on the overall energy efficiency. And a similar use case in this context was devoted to a battery electric vehicle with a focus on the thermal management, system layout and optimization, so the battery conditioning and passenger cabin heating and air conditioning. And the third use case out of this cluster was devoted to heavy-duty truck hybridization, where different hybridization variants, 48-volt and 400-volt hybridization, were investigated with respect to the performance and emission characteristics. Use case 3, the post-Euro 6 after-treatment system matching, looking at phase change materials and heated catalysts was investigated with the Vision XEV framework, demonstrating its applicability and demonstrating its impact on efficiently performing parameter variations and without the need for excessive experimental input and data. On use case 4, different configurations were virtually analyzed for the heavy-duty hybrid truck configuration by adopting the battery e-machine thermal management models from the partners and using the Vision XEV framework methodology. So regarding the mid to long-term impact out of Vision XEV was already highlighted and demonstrated by the partners based on the use cases that based on the framework, improved integration of the engineering suppliers and the research partners is possible with the developed framework and the open interfaces and co-simulation technologies, which will contribute to an accelerated uptake of innovations in the future. The Vision XEV activities or results and achievements will also contribute to the further virtualization of the development processes, and by also enabling further front loading of development activities. And by that, there's a good potential of further reducing hardware prototypes and hence to reduce development iteration cycles and considerably reduce time to market. And yeah, and generally the development efficiency of multi-power platforms of complex hybrid systems will be largely reduced according to the impact assessment performed by our industry partners. Well, regarding the expected market uptake and future research needs, so we are utilizing the results and achievements in ongoing and future research and innovation projects, so that on the industry side, on the academia side, results have already been included into the teaching activities, into the lecturing processes, and the know-how gain will also contribute to the ability of all the partners to set up new and subsequent innovation projects. Well, as already mentioned, the adoption of the Vision XEV methodology will be used also at the OEMs and at the engineering and hardware suppliers for better integration of the research and technology suppliers into the product innovation process, and by aiming at future hybrid and virtual product releases to reduce the hardware prototypes. Well, and on a midterm or as an outlook, so a next logical step would be the expansion of the Vision XEV framework towards application to virtual heavy-duty fuel cell electric vehicle development, which is currently a very, let's say, important technology activity or initiative in Europe. And I think also the topic of internet and cloud-based virtual co-creation, adopting artificial intelligence and machine learning is also something that could be a logical next step of the Vision XEV framework achievements, perhaps in combination with what we have heard before from Ella, what was obtained or achieved in the Panda project. Yeah, with this, I'm at the end of the presentation. Sorry for being a bit longer than planned. Thank you.
Automotive Engineering Group as the coordinator and principal investigator of several European industrial academic projects, and Marie Slobodowska Pure Reactions. Valentin is a SAE Fellow, a Alexander von Humboldt Fellow, a member of the Society of Automotive Engineers of Japan, and of the Association of German Engineers. Valentin has received the SAE Ralph Titor Educational Award and the CAD-LM Intelligent Optimal Design Prize. His research fields are vehicle testing, electrical vehicles, and automotive control systems.
Thank you, Eric.
Thank you very much, Valentin. The floor is yours.
Thank you. Good day, everybody. It's my great pleasure to to discuss with you today the project XIL for EV. I'm sorry.
No?
I don't know.
No, no, it will work. Yeah, yeah.
Okay, thank you very much. Our concept has emerged several years ago after discussion. What for new testing and validation tool can come after very well-established methods like software in the loop, hardware in the loop, and model in the loop. After discussion with our industrial and academic partners, we have come to idea that maybe next powerful step will be if you will unite in one network different testing facilities to perform simultaneous synchronous experiments. In general, we can now speak about concept of test rig in the loop, but with addition of software and modeling components, we can speak about X in the loop in general. In our case, we should follow two important features. The first one, we are speaking about testing facilities located in different geographical locations. Second feature or requirements is all these facilities should perform joint experiment in real time. Of course, these requirements have put many technological obstacles like time delays, if we will connect by internet, for example, data losses, response of actuators on test rigs, and so on. To answer all these questions, we have prepared our proposal, XIL for EV, and formulated a number of objectives indicated here. And we have also decided to demonstrate this approach for several use cases addressing electric vehicle system design. Some complex design cases like brake blending, integrated chassis control, as well as fail safety. All these use cases are united by the same concept of architecture. Here we have several layers of X and Z loop environment, software, communication, and so on. And this layer are communicating between each other and also between different test rigs. This global architecture can be realized, at least we have demonstrated in the project, by two ways. In first case, we are speaking about the called local X and Z loop environment. It means we are uniting several testing facilities located not so far away from each other. Examples can be campus facilities or industrial factory facilities. In the project, we have united, for example, in-wheel powertrain test rig, brake dyno, and hardware in the loop test rig for testing chassis and brake components. And with this architecture, we have investigated, for example, brake blending operation. Definitely more complex case is remote X and Z loop environment. Here you can see our example. We have connected the driving simulator in Netherlands, suspension shaker in Spain, and powertrain and brake dyno tests in Germany. And you see here really big distances, but with the help of our technologies and using our network configuration, we have achieved, I will say, quite acceptable time delays, which allowed us to perform a really real-time experiments for complex automotive control systems. What we have investigated with these two X and Z loop environments. The first use case was dedicated to the brake blending. As you know, we need a joint operation of electric powertrain and friction brake system, and it is really time-consuming by industrial companies to perform different tests. And we have optimized the brake blending controller of Audi e-tron with the help of this X and Z loop environment. Next use case was definitely more complex. It is about integrated chassis control of electric vehicles, where we need a joint operation of in-wheel motors, friction brake system, and active suspension. And also, our X-loop environment was able to perform a controller tuning and design in quite optimal way and in very short time. I would like to show you short video. Here, simulation environment in real time is put on the driving simulator in Delft. In-wheel electric motors is here in Germany. On left side, on right side is the chassis shaker in Spain, and in real time, simultaneously, all test rigs are working to perform one or another test. In this case, it is like integrated chassis control by obstacle avoidance. This will be repeated again. Okay, and extra case was dedicated to fail safety issues. For example, for such companies like LAFE or consortium partner, it's very important to test fail safety algorithms for different powertrain topologies. And it is quite hard to have all possible topologies on one vehicle demonstrator. In this case, we will put some topologies by other partners. We can perform a really online investigations on fail safety algorithms as well. What we have achieved with these results, in my opinion, one of the most important impacts is related to industrial components. We could essentially reduce development and design time in accordance with estimations of our industrial partners, depending on the system and function. We could expect a reduction of validation and testing time from 20 to 50%, and with overall cumulative effect, it's of course is definitely higher as target 20-25% of overall development time. In addition, with online real-time experiments, we could receive extra benefits regarding the costs, as indicated here. But in my opinion, maybe the most another very important impact is contribution to the concept of open research and open science. As you know, we have many good research teams in Europe, in world with limited access to testing facilities. By integrating different research groups in X-loop environment and giving access to complex experimental equipment, we could definitely in future receive extra positive results, I believe. So it was all information. If you will have additional the questions, you can contact me by email. Thank you very much.
Thanks a lot. So welcome also from my side. I have the great pleasure now to round off a little bit this interesting session. I would say thanks a lot once again to all our, thank you. Thanks, Lucy. Thanks a lot to all our speakers. I would say, just to introduce myself, Aldo Offenheimer, virtual vehicle from Graz, Austria, focusing in my research also on the virtual vehicle development. That was a perfect match, helping, so to speak, for this session. And looking time-wise, I said 3 bullets, which I took from my side, maybe just to kick off a little bit the discussion. I was impressed seeing a lot of figures, but this specific call was really saying, what could we save in terms of product development time? And we have seen efficiency gains up to 25%, reducing development times by 20%. And the last one, quite interesting, by this, I would say, this remote testing, up to 50% time savings. just trying to connect remote testing infrastructure. So the floor is yours. Happy to take your questions and then pass it on to our presenters. Questions? Any questions?
Maybe I can start.
Yeah, Sisi, thanks for breaking the ice.
To break the ice. Thank you. This is Amaras from Aristotle University. I would like to ask two questions, actually, to Mr. Busquerol from Panda. My first question is, you talked about portability of your approach to other platforms. And you mentioned Amasim and MATLAB, I guess. How easy is, for example, to incorporate it into CruiseM, for example, platform, or to Gamma Technologies, for example, GD Power? How much work is it necessary? That's my first question, and the sub-question to it is, are you using FMI, for example? I mean, this should be done by FMI, or how? And what exactly your technology, how your technology, ERM or EMR, sorry if I got it wrong, yeah, differentiates. And my second question, the second question was about, are you taking into account aging phenomena? I mean, are you in the position to simulate long-term effects, for example, battery aging into your simulations? And if yes, how? Thank you.
That was a sophisticated two questions, but Panda will take it.
Okay, thanks. First, about portability. In fact, we use also another tool, which is Typhoon for real time. They develop during the project the library. And what is interesting is that finally we have coupled both software, AMSIM and Typhoon simulation tool, thanks to the method, without FME. The interest is also to organize the software in a way that we have not to reorganize using FME. And for real time, it's really interesting because you know that FME is a supplementary layer that leads to supplementary computation time. And due to that, what I presented, the cloud was in AMSIM, the real-time simulation was in Typhoon simulator, and they communicate thanks to the way to organize the method. One of the problems is that it's another philosophy of simulation. That means that it's not the classical one. The classical one is called structural organization. You have a library of components, you pick and place, and you connect as in the real life. In that way, we have to reorganize the model with specific rules to be sure that any time we have exactly the same input and outputs anywhere in any software and so on. That means that you need sometimes to prepare the simulation, but of course you gain after. So it was portability and FMI. And another interesting point is that we do the test in Valeo company, but Valeo company has not the same software and the same real-time simulator. We use DSpace and we use MATLAB Simulink, but the transfer was automatic, in fact, and we do that automatically. So we spare a lot of time to organize, but at the final stage, we have a real gain. So aging, yes, we do aging of a battery with a VUB and also University of Lille. Of course, the time, the simulation time is not the same. That means that we cannot do that for the moment in real time. But offline, we just replace the classical electrothermal model of the battery with a more complex battery with aging laws, but exactly with the same input and output to be connected to other parts of the ancillaries, the electrical drive, and so on. What is the interest to do that?
Thanks a lot. Any other questions?
You have a question?
One? Christoph.
Yes, so Christoph Scharnus, FEV and EAPA. So, first place, thanks to all the presenters for really interesting presentations.
Just a little bit higher.
Yes, and my question would be, in the first place, Alain, I fully agree with you. So when you're putting models together, talking in a picture, you have to make sure where are the screws and where are the threads. So if you're putting, yes. And I think, Reinhard, thinking back to the projects Obelix and HiFi Elements, we had agreed upon a certain standard or between us how to make models exchangeable between the two different platforms. So my question would be, does your project now build up on the platform that you have created in Obelix? And how far did you maintain the previous interfaces? And a third question would be, what was the latency of the network that you applied for the multi-site simulations when you coupled the simulations in real time in the different places? So what was the time base that you managed to have the different simulations or the components interfacing with each other?
Okay. Thanks a lot. I think, Reinhard, the first part definitely goes in your direction.
No, I think it works now.
Yeah, it's working now.
Does it work now?
Yeah, it works. We can hear you.
Well, regarding the results, the achievements from the previous project Obelix, they have played a role and they found their way into that into Vision XCV, and things were extended according to the much broader scope of work, and were adapted also to the, let's say, to the latest FMI, FMU standards. And so I hope that answers the question, yeah.
Maybe on the topic, thanks, Christophe, because of course we have a look in depth of if element and Obelix in order to know what are the trends and so on. And it shows that if element propose a standard organization, we are close to that, but we respect strictly the integral causality. That leads to another philosophy, but it shows that you demonstrate that it's very important to impose strict input and outputs. It's not so easy in different software, but we have to do that. And it's an extension of that, of course.
Yes, okay. We have experienced it at the beginning. We find solution our test rigs are in same in virtual private network with allocated IP numbers. In the case of local XIL, for example, we tested in Campus Ilmenau on the factory of Audi in Ingolstadt. From T-space to D-space was quite good, 2 milliseconds. Between Germany and Netherlands, depending on conditions, maximum 10. I will say the worst cases, we tested the space, but 2D spaces in same virtual private network between Germany and Japan. It was 100 milliseconds. But even 100 milliseconds can be considered as soft real time, and for several control design tasks is applicable, I will say.
Yeah, if there's one follow-up, we have a little bit more time because the next session is late. If you would like,
Yes, no?
you can go on. We have some more minutes. I just was told it's possible.
So the main problem with, let's say, having large time bases for the interface between two different simulations is certainly that in a physical system, you have the immediate response time. So that means you may introduce some instabilities in a feedback between the different components. Yeah. or some artifacts that cause some noise on otherwise in the real system smooth transitions between states.
We do have time. You would like to react on that? Well, it was, I think, was more a comment in this direction. Yeah.
Maybe I can add something, because in fact we experience that only cloud and testing is not two-side. But what is important also is to include safety process in order to stop in the right way the experimental setup if there is some power issue, of course, but also if we lack the connection. So there is also some specific development to ensure safety.
We could take one more question. Yes, Eric. Now the floor is yours.
Eric Amago from AVL and at the same time coordinator of EVC 1000 to be presented tomorrow. And my question was not directly a question, but a kind of request. So just to support my presentation for tomorrow, in terms of collaboration between the projects. So here, so we have especially Vision XCV. So with two projects coordinated with AVL. We have XIL, XIL for AV with here that collaboration in the project. Can you please elaborate a little bit about the collaboration between the project and the advantage for both projects, so for all the project, for all the community in this direction?
Yes, please.
Okay,
Just
yeah.
on whoever
I will
takes.
say, actually, we have a very useful collaboration between XIL4EV and EVC 1000, which will be presented tomorrow, because we have even three industrial companies in same consortia. It's Audi, Halafe for in-wheel motors, and Technico for active suspension. In EVC 1000 is exactly quite complex task for integrated vehicle dynamics control, where we need to organize a joint operation of powertrain and chassis system. And for this purpose, to avoid extensive road tests, XIL4EV is giving a really good tool for very short-term optimization of the controller. Therefore, for us also cooperation was very interesting to validate our concept.
Additional comments on that from the panel? Yeah, Reinhard?
Thanks to Alain. We had several workshops in the framework of the VPPC Congress, and also a special session was co-organized by University Lille and AVL on e-components modeling. And I think that contributed a lot to a lively exchange of information and regarding activities, and so that was very fruitful for us, and I hopefully also for University of Lille.
Yes, it shows that at the beginning we built an independent project, and as said by Eric, finally is really complementary, and we discover it's order. And finally, what we discover is that Vision XCV is more related to the development axis of the V model. Panda is more on the virtual axis, and XIL4EV is more on the testing axis. So now what is the next step? The next step is how to build a complete set, coupling all the projects in order to give a real interest for company to use a global vision of that.
Thanks a lot. Eric, yeah, something to add?
Maybe a last short comment from my side. So here we have the chance to have set up a follow-up project in this context, more in the new component. Really looking forward for the outcomes or the sustainable outcome of the three projects and the capability to use all these different methodology in new project to be started. Thank you very much.
Okay. I would say we have time for one more question. I think one final question. Eric, now it's not you. Okay, just behind you, Lucy. It's easy. You don't have to run.
Hello. Well, my name is Mikel. I was just curious about the start date and the end date of the project. Maybe it's the start date and the end date of the project.
Okay, that's easy. I think the start date and the end date of all your projects to see a little bit the time overlap.
So Vision XCV started in January 2019 and ended in December 21.
For Panda, we start in December 2018, and we have 6 months more due to the condition of COVID, and we will end in May.
Yes, and we have started in January 2019 and finished December last year.
Okay, thanks a lot. So now I take the liberty for one final question from my side, because I was just waiting if there is time, and that was going the direction, I think, especially to Reinhard. I think on one of your slides, you were saying hybrid and virtual product release to reduce hardware prototypes. Looking in the crystal ball, when do you think this might become reality? That we are really looking or having, so to speak, virtual product release? It's not an easy one.
I'm not going to tell you here any concrete year. Otherwise, my colleagues
will not be too happy.
Will not be too happy. But there is certainly some time to go. Yeah, but it's
is it feasible? Because it was interesting.
It is,
so to speak. So it
according
something more
to the feedback we got from the OEMs.
Yeah?
It is. Something they are heading at, and that is something. And Vision XCV is one building brick into this direction. Yeah.
Thanks a lot.
It's still some time to go.
Okay, good. So that's okay. So I do have. So it was not a fun. As I said, we are so happy, so to speak, that we have some more time, because the next session is a little bit shorter. I think that's the point, isn't it?
But still, the ones that have not yet finalized.
They are not so punctual as we are.
We are trying to align.
Yeah, no worries. Yeah. Yeah. One question from your side, or is it just no? Okay. Any? Yeah. Okay. The coffee question. This is then the last one. One final call for a final question. If this is not the case, I would like to say thank you again to our colleague, let's say from the Commission, to our 3 presenters. And I would say you have the best chances to get a hot cup of coffee, because you will be the first, because we are a little bit earlier than the others.
Yeah, not sure there is coffee really during this break, because it was planned to be only 5 minutes. But, well, you're more than welcome to check if there is still some remaining from the previous one. And you have here, just here, the list of the upcoming sessions. So if you want to attend the next Green Vehicle session, you can just stay in this room. If you are attending one of the other sessions, I will just ask you to wait in front of the room so that the other can finalize the discussion and we don't disturb them too much. Thank you very much.
Thank you. Thank you.